Okay, so, well, as I said before, I'm going to try to summarize the cost and compare a little bit between the different simulations, CPU, GPU. So, well, the motivation, if here I have some numbers that Neil shared with me. These are numbers from AWS. Perhaps they are not perfect. We could get some others, but they gave us some idea of the cost of the different CPUs used and the different GPUs. The cost per CPU are per core, because if we had machines that had 90 cores and ones with 12, it was very different. So for the cores, the prices are more or less the same, 5 cents for Intel and 2.5 for AMD, more or less, all very close. There are some in blue that Neil didn't find, so I approximated close to the one that I considered most similar. Perhaps there is an error, but well, this is the first iteration of this kind of quantitative assessment of the different runs. And then we have the GPUs. We see that H100 is very expensive. Then we have A100, B100, and L40S. He had L40S, not L40, that supposedly is a bit cheaper, but well, it's an approximation that we have to make. And then the A10 that is quite cheaper. And well, there are two cards that are more like not professional, commercial, but they should be the kind of software very similar. The 6000 ADA should be very similar to the L40, at least close to the L40S. And actually, the GTX 3060 is actually even poorer than the A10G, but well, I didn't find any other card. So well, and then we look at the cost in dollars, multiplying for 80 convective time units. I didn't look at how much everybody can run. I put just 80 convective time units, and with Neil, we considered it was acceptable for a converged simulation. And this is what we have from $10 to nearly 100,000. Somebody will have to pay. Well, so looking at the results like this is very difficult. So I try to look at the results from different angles, and I will try to get some idea of what is happening. So, well, we also see that the number of time steps per convective time unit are very different, from close to 100 to close to 100,000. And so obviously the costs are going to be very different. And this is just the time step size. We also have the mesh size. So obviously it's very difficult to compare. And I will look at two things: cost, that is the money that you would pay, and also speed, that takes into account scalability. If you can run in more GPUs at the same time, or more CPUs, then you can have your results overnight. And this is also an advantage. But I guess for the industry, the most important one is cost. So we start with cost, and I will use two measures: computational time per cell and time step. Yeah. So this is, you got your wall time per time step, and you divide by the average number of cells per GPU. Alternative, that is the same as you get your wall time, multiply by the numbers of GPUs, and divide by the number of cells. Well, I put here GPUs. In the case of CPUs, I do it with cores, so the results are separate, and we can put them together when we multiply by the cost. Yep. Well, this is the inverse of what is called million updates per second. Yeah, with a factor of 1,000,000. So, well, it's more or less what is typically used. The advantages of this approach: it allows to compare meshes with different degrees of freedom. So very big meshes and very small meshes should be more or less comparable. If you are within your scaling range, it also allows to compare meshes of very different sizes, and the values should remain more or less constant. Disadvantage: it makes little sense if you are comparing strategies that are very different. If you go to an explicit code and then you go to an implicit code, or you have a finite difference compared to an unstructured grid, it's not comparable. Well, in the implicit case, it also will depend on the tolerances that you use, the number of iterations. So, well, it's not perfect, but it's one way of seeing at the results. And so here I plot the results for the GPU runs. Yeah, and well, what can we see? first thing, for example, here we have all these results clustered together, and this is nice. When we look at this from other perspectives, these that are in different size of meshes with different degrees of freedom per GPU, they spread out. This, I believe, is a more representative value of the behavior of the code. Yeah. And then we see like two different groups. Here we see these values that are very, very fast per time step. So these are the lattice Boltzmann code at a finite difference code. They are all close to 1 nanosecond per degree of freedom and time step. Yeah, so these are the results over here. This is results that I will use quite a bit. It's exactly the same mesh with different GPUs. Yeah, and this is will allow me to compare between the different GPUs. They also provided results with CPUs, so this is perhaps the best that we have to compare different hardware. What else can we see? Well, and here we also have in the first column, it's ID number 2. They use like two very different strategies. So if you look per time step, they are quite different. But when you look at the end in the total run, they are very close together. And then we can also see two different participants with the same code. And well, their results again are very close, despite the meshes were, I believe, also different. So well, this is one way to look at the results, and I put here both Driver and Windsor. You have different colors for the different cases. When we look at these same values for the CPU, well, the Y scale it's not comparable because we cannot compare a core against a GPU. What we see is that most of the results are in this range. We have the lattice Boltzmann code that is very fast, yeah, per time step, but it has very small time steps. And we have there a Cartesian method that is also quite faster than the rest of the code because it's a finite volume method, and because it's Cartesian again. So, well, this is where we see the CPU results. And then multiplying by the values that I showed in the second or first slide, we can put this into dollar cost. Yeah. And well, here we have the different codes. Again, we have the lattice Boltzmann code down here. Well, we see here the different GPUs. The L40 is the cheapest one, the most effective one. The H100, despite it's very fast, it's very expensive also. Well, they run A100 with two different loads per GPU. Well, it's not scaling perfectly, but it's very acceptable. So these values are very close. What else can we see? Well, below this line that I chose more or less a priori, we see that we only have two CPU results. So, well, yeah, clearly this indicates that GPUs are more effective, as all of the people that have tested GPUs are sure that GPUs is the way to go. Well, so this is a general observation. So, and then this we have the problem of the time step in the previous. So here, perhaps it's better to look per convective time unit. So we just have the previous value and we multiply by the number of steps per convective time unit. And well, this can be more interesting to the industry. It is similar to what some other people told me that they use computational time per 1 million cells and 1 second of physical simulation. So you just get this value multiplied by the number of time steps you have in 1 second. 1 second of 1 convective time unit, well, it's just a factor, and then you introduce other factors. It's better to use convective time unit because I have Driver and Windsor. If not, it wouldn't be comparable. Well, but here it makes the comparison between different meshes very difficult. Yeah, so these results that before were all clustered together now are very spread, and this is not a worse simulation than this. It's the same code, and the other value is the one that gets the real information about the code. And since since when we use this value, we depend a lot on the time step that we are using, that is typically coupled to the mesh. You have a coarse mesh, you have a bigger time step. Perhaps it's better to look only at the results that are in committee grids that I have marked there in blue for the Riviera and one also for the Windsor. So this is what we can see. And well, we can do similar things for the CPU runs. Again, this is the results that we got. And finally, we can multiply by the dollar cost as we did in the other case. And again, well, now we get these results that have some spread. In general, GPUs are a bit better than the CPU. Yeah. And finally, we can go to the results in the real mesh and try to put some information to make this comparable. So this is the dollar cost for 80 convective time units on the real mesh. So we have some values here that are really very cheap, but well, they are coarse meshes. It's difficult to compare with the other results. So we have marked in blue the results that are committee grids, and actually there are some with not dotted line in blue. They are very similar to the committee grids, very similar number of degrees of freedom and time step. And when the results with the lattice Boltzmann have gone up, and they are quite close to the results with the finite volume. So we are in this range. This range goes from $300 that we have here for participant 22 to around $5,000. Well, this is what we have, and well, this is what we can show. And then finally, we can go to speed. This would include the scalability. If you can run in less number of degrees of freedom per GPU, you can run faster. So we can look at this per time step. And well, here, well, you see that you have different load, and you will get different time per time step. And finally, perhaps what is more interesting is the wall time per convective time unit. Yeah. Sorry. And here we can see a full picture of the results. We can see that perhaps this is one of the nicest results that we get. It's taking a little bit less than 3 minutes per convective time unit. This is, well, like very spectacular results. We can have these 80 convective time units in less than 4 hours. Yeah, well, you can compare with some other codes. It has a, well, more or less big time step, but well, actually they showed that they reduced to half the time step, and the results were very, very close. Yeah, they also have a relatively low load per GPU, only 3.2 million cells. Yeah, and also a very small time second per degree of freedom. And so I compare it with some other code, yeah, that has a very similar mesh, but it's a bit slower, or twice the time per degree of freedom and time step, so 85 to 170 nanoseconds. It's running with a bigger load. I don't know if they could actually go lower. We haven't done real scalability analysis. And then they use a smaller time step, just half the time step, but well, you multiply 2 by 2 by 3, and it's a 12 times difference. This is what I can say. Well, and then typically the finite volumes were a bit faster than the lattice Boltzmann, despite they are very fast per time step. They have to run smaller time steps, but also typically they work with a bigger load per GPU. We haven't done real scalability analysis. Perhaps they could go to lower loads, but well, in the results that we have shown, typically this is what we have. And well, this is more about it. So, well, the time steps, this is another result that I want to highlight. This is a measure that is very close. It has also got a very good time per degree of freedom, just 20 nanoseconds, but it uses a much smaller time step. So, well, these two results are quite interesting to me. So the conclusions. GPU simulations are faster and cheaper than CPU simulations. Everybody that has tried it is clear about this. The choice of GPU can have a big impact on the cost. So typically here we saw that the L40 is like the best GPU for our HPC things. Perhaps our AI H100 can be a better option. Then we have to say that if you run this in your local machine, typically a commercial card would be much cheaper, but well, we do not introduce this other price effect here. Finding difference and latency response one are very fast per time step, but then you have much smaller time steps, and on top of that, in the results that have been submitted, typically they use a much higher load per GPU. Well, we have a big variation of time step sizes, even with the same grid, and this makes the comparison of the cost quite difficult. I would be curious about a deeper analysis of the influence of grid refinement. And well, this is all that I can say. This has been part of an European project that I cite below. Thank you very much.